In the last video, we were looking at evaluating line integrals of scalar fields, and we looked at how we can go about doing that. In this video, I want to look at a specific example here. So we're looking at this integral and we want to evaluate it. So we have the line integral of x minus 4y, and then dx, minus 7y squared, and then dy, where c is going to be given by x equals y squared plus 6, moving from the point 7, 1 to 70, 8. So before I go into this, I just want to break down what we're looking at here. So here we have a combination of coordinates. We have dx and dy. Now, at its face, it looks very confusing because normally we don't see two different differentials when we're trying to evaluate an integral. But as we talked about in the previous video, if we look at it step by step and substitute the correct parts into it, it's actually very doable and quite easy. So let's go into this. So the first thing I would want to do here is I want to parametrize C. So this process might seem a little bit complicated, but if you follow along, it's not that bad. So C is given as x equals y squared plus 6. Our goal is we want to rewrite the x values and the y values with some new parameter t, such that when we combine them, we're still going to get back the same curve C in the correct orientation. So for example, I might say y of t equals t, and x of t is equal to t squared plus 6. So what does that even mean? It might seem a bit complicated at its face. Essentially, the idea here is if I pick any value of t, for example, I might pick 1. If I say, what's y of 1? Well, that's just going to be 1. And x of 1, well, that should be equal to 7. So I generated a point 7, 1 from the parametric form. And if I look at the form that we were given in the question, if I put in 1 as y, I'm going to get x to be 7 as well. So as you can see here, these two forms are really interchangeable. But this is the form, the parametric form is the one that we want when we're trying to evaluate this integral. Now, I want to emphasize this because it's quite important here. When we're talking about y of t and x of t, these need to be equations only of t. We don't want any other variables here. We can have constants, but we don't want any other variables. So once we have that, we'll see later why this is very important. But the next step here is let's just compute the derivatives of y of t and x of t. So let me go back to the other color. So y prime of t is just simply 1, and x prime of t is going to be 2t. And those are the derivatives there. Now I'm just going to do this piece by piece, and then once we put everything together, then you'll see why I'm doing all of this. The next step here is to fix the bounds. Fix the bounds. This is something that it's very easy to forget, and you can get a question wrong if you forget to do this part. So in the question, if we go back here, C is given, or we want to integrate with respect, or we want to integrate the line integral of C from 7, 1 to 70, 8. So we have here 7, 1 and 70, 8. Now in truth, because we're given the equation, we didn't need all of these points. We could have just been given the x bounds or the y bounds. But this is just more information for us to work with. So the 7, 1, as we know, this is referring to x and y, and then another x and y. Now this would be very useful if we were integrating some sort of function with x's or y's. But remember, we're not. We're trying to convert it to an integral of t. So we want to know bounds in terms of t. So how do we convert that? Well, we just generated the equations up here. We said that y equals t and x should equal t squared plus 6, those new functions that we created. Now, the simplest thing to do here is just to rewrite these bounds rewrite the y bounds rather in terms of t because they're equal. Y is equal to t. The function y of t is simply just t. So that means since y of t is just t, we can then have new bounds where t is going to go from 1 to 8, just like the y bounds up here, because this means the same thing. Now again, as I mentioned a little bit earlier, if I said the x bounds are 7 to 70, the y bounds are 1 to 8, or the t bounds are 1 to 8, all of those three statements are identical because of how we define the variables in the equations up here. So now, let's substitute all of these pieces together and see what we have. So that's the next part here. We want to substitute. So, remember, we're going from a line integral to a definite integral. So, the first thing here, we want to rewrite our bounds. So we just talked about it here. We're going from 1 to 8. So 1 to 8. Now, what does our integral become? So let's go back up here in the previous video where we were looking at substituting parts in. If we saw an x, we want an x of t. If we see a y, we want a y of t. And in this case, we don't have an arc length, we have coordinates. So the dx should be x prime of t dt, and the dy should be y prime of t dt. So let's do that. So in the question gave us here x minus 4y. So what is x going to be? Well, x is this now, t squared plus 6. What is y going to be? Well, y is just going to be t. That's what we said up here. Now what is dx? I can just rewrite it here just so we have it. Dx is going to be equal to x prime of t dt, and dy is going to be equal to y prime of t dt. And x prime of t is here, and y prime of t is right here. So now let's put that all together. So I want my x first. The question said x minus 4y. So x here is t squared plus 6. So let's put that here, t squared plus 6. Then we have minus 4y. Well, y is just t, so then we'll say minus 4t. And then we have dx. Well, what's dx? X prime of t dt. And what is x prime of t? It's 2t. We said that up here. X prime of t is 2t. And then we'll put in the dt. Now we have another part here. We have minus 7y squared. Again, y is just t. So we'll have minus 7t squared. And finally, we have dy, which is just y prime of t dt, but y prime of t is just a 1. So it's just 1 dt, or we could have just said dt. Now, this might seem very confusing, but notice what I did. I went through this step by step, and I kept referencing the initial line integral and converting it to the definite integral piece by piece. And once we have it all written out like this, it's less likely that we're going to make mistakes when we compute this. Now, how do you know if you made a mistake at this stage? Well, I should only see either t's, functions of t's, or constants in this equation. And there should only be differentials of t for the case we're talking about here anyways. If there was an x or a y left in here, I didn't substitute everything in completely. So that's the way that we can check and we can make sure we're doing this correctly. Now the last thing here is simply to integrate. So we want to look at this and we want to make it a little bit simpler because right now there's two differentials. It's a bit confusing. So here there's a number of ways that you can integrate this, but this is the way I think is probably the easiest. Let's factor out that dt, because we're now integrating with respect to t for this first function, t squared plus 6 minus 4t, and also the minus 7t squared. So we don't need to have those separated, we can combine them. So we'll have the integral from 1 to 8, 2t cubed. I'm just distributing the 2t into that bracket. So 2t cubed plus 12t minus 8t squared. And then I'm going to bring that minus 7t squared into here. Minus 7t squared. And then, of course, we have the dt. Now we can simplify this. Before we integrate it, we want to just combine all the terms that we can. 2t cubed minus 15t squared plus 12t dt. And now we're ready to integrate this. This is a very simple function to integrate. So we have 2 over 4, or 1/2, t to the 4, minus, we'll have 5t cubed plus 6t squared. So that's going to be the integral of that initial function we have up here. And we want to evaluate this from 1 to 8. And now it's very simple. We just want to plug everything in and evaluate it. So we have 1/2 times 8 to the 4 minus 5 times 8 to the 3 plus 6 times 8 to the 2 minus, remember, we're subtracting the lower bound, 1/2 minus 5 plus 6. Now if you work that all out, which you can do and multiply it together, you'll get minus negative 129.5. And that's the answer to this question. So remember, the whole point here is that we're trying to go from a line integral to a definite integral. Now this was a combination of coordinates. In the next video, we're going to be looking at the arc length if we want to integrate with respect to the arc length.